report the measurements that we took in the lab last week for the refrigeration cycle. So this is what I'm going to go over: the synopsis of theory of the experiment, presentation of raw data. I'm going to discuss the results and conclusions. So here's the background. This is how heat pumps work. And the main goal is to take heat from a low temperature source and inject it to a higher temperature source. Evaporator, expansion, condenser, and compressor. The refrigeration cycle process has 4 main steps. First, compression, where the refrigeration is compressed into a high pressure gas from 1 to 2. And then condensation, where the gas releases heat and turns into a liquid from 2 to 3. From 3 to 4 is expansion, where the liquid refrigerant's pressure drops, causing it to cool. And from 4 to 1 is evaporation, where the refrigeration absorbs heat and turns back into a gas, completing the cycle. So here's a review of your Carnot refrigeration cycle. It is the most ideal cycle. It assumes no losses, and there's isotropic compression and isothermal heat transfer, and your real refrigeration cycle will have losses. Your coefficient of performance can be greater than 1 for refrigeration cycle. COP measures the performance of your cycle. COP for real cycles can be calculated with enthalpies, or which is your H's, and if you already know your heat and work compressor, then you can just divide those. Your Carnot COP can be calculated with 2 temperatures and use the temperature differences. Your Carnot COP will be greater than your real refrigeration cycle COP. From the experiment, the goals were to find the inlet power, the produced heat, and the COP. In the lab, we had to, for the second exercise, we had to change the flow rates at the evaporator and create pH diagrams and calculate COPs for different variables. For the setup, it's right here. They have little numbers next to them to label them, and the compressor is in the middle, right here, and the condenser is on the left, and the evaporator is on the right. And there's about 14 sensors throughout, and you're going to have R134A fluid going through the system. And there's 2 pumps at the bottom. We're going to zoom in on the thermal expansion valve up in the corner, number 14, and it regulates the refrigerant flow into the evaporator. And this achieves this through sensing the inlet temperature of the evaporator via a sensing bulb and changes the valve opening as needed. The objective of the TXV is to decrease the pressure in the evaporator so the coolant boils at lower temperatures. Here's what it looks like in real life, and here's a diagram showing you this is where the refrigerant will go, and it will flow through here, and it will regulate whether it should be open or closed. So from the lab, this is the raw data from exercise 1 and the uncertainty values that I calculated. And these are the calculations. So we got the work, the power consumed by the compressor, the temperature at the inlet condenser and the outlet of the condenser. And we also got the water inlet flow at the condenser. And then I calculated the heat of the condenser and the heat pump COP. So there's a little bit of difference between my sample calculation from last time and the raw data, but that's because the work were different, and yeah, this would be about 1 higher. From exercise 2, here's the raw data, and exercise at the different, this was at the different flow rates, so we started with 6 liters per minute, then 4.5 liters per minute, then 3 liters per minute. There wasn't much difference in the pressure and the temperature, and that results in the graphs being pretty similar for each one. So I calculated the or found empties from the charts in the lab manual for R134A and put into MATLAB, and I got this diagram. It's pretty much the same for each case, and the COPs were decreasing, so it started with 5, then went to 4.67, then went to 4.34, so not much change. Some errors could have been the insulation was not very good. There could have been a delay when the group member adjusted the knobs, and the computer response changed digitally, and the sensors may not produce precision when group members take measurements, and there could be leakage in the compressor. In conclusion, the states of the refrigeration cycle resulted in expected outcomes. Increased COP, compressor work input must be reduced, and the results show sensitivity of COP with varying operating pressures and temperatures, and effectiveness can increase by minimizing energy losses with sufficient insulation. Any questions?